Welcome to the module Understanding Redundancies. In this module, you will learn about redundant systems. A redundant system is the system with redundant constraints, or in a simple way, over-constrained systems. Redundant constraints occur when more than one mate constrains a specific degree of freedom on a part. In this module, you will also learn how redundancies affect the motion study and how they can be removed. In this module, you will learn how redundancies affect motion studies. You will also learn how to use flexible mates to automatically remove redundancies in a mechanism, assign the stiffness to each mate, and understand how to build assemblies without redundancies. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. Any unconstrained body in space has 6 degrees of freedom, 3 translations, and 3 rotations about the x, y, and z axes. When we connect rigid parts together using mates, each mate removes a certain number of degrees of freedom from the system. For example, a hinge mate between 2 parts will remove 3 translational and 2 rotational degrees of freedom, which means it will remove total 5 degrees of freedom. This also means that hinge mate will allow 1 rotational degree of freedom. The table on screen lists the most common mates along with their effect on degrees of freedom of connected bodies. The table on screen lists some of the special mates, which do not necessarily represent a real mechanical connection, but can affect the degrees of freedom of connected bodies. Based on the number of degrees of freedom, the mechanical systems are divided into 2 categories: kinematic systems and dynamic systems. Let's understand what each of these means. Click each tab to learn more. Kinematic systems are fully defined systems, which means that different parameters, like displacement, velocity, and acceleration, of each and every component of the system are fully defined at each time step. Therefore, this type of system has 0 degree of freedom. For such a system, the resulting motion does not depend on the applied forces and mass of components. For example, consider a scissor lift. The motion of the scissor lift will always be the same regardless of the mass of the links or platform or the weight of people standing on the platform. Only the force required to drive the lift will change, depending upon a change in the mass of any component or the external load. More weight means that more force is needed to get from height A to height B. In a dynamic system, the resulting motion of parts depends on the mass of components and applied forces. If we change the mass of the components or applied forces, then the resulting motion of each part will be different. Such a system has degrees of freedom more than 0. Consider the mass string example. In this, depending on the mass of the balls, the motion will be different. Or, if we swing the ball on the left with a different force, the motion of the balls will be different. Redundancies are unnecessary constraints. Redundant constraints occur when more than one mate constrains a specific degree of freedom on a part. When we solve a system having redundant constraints in SolidWorks Motion, the solver will automatically remove the redundant constraint. However, in complex situations, it may not remove the correct one for the mechanism affecting the original design. Consider the example of the base and link. In this case, 2 hinge mates have been added between them. The additional hinge mate constrains the same degrees of freedom as the first hinge mate. Therefore, there are 5 redundancies. Before a simulation is run, The solver goes through the process of detecting if the mechanism contains redundancies. If it detects redundancies, it will try to remove them. If successful, the simulation will run as normal. Else, redundancies are evaluated and potentially removed at each time step. There is a certain hierarchy by which redundancies are removed. The solver will remove redundancies based on the following order. 1. Rotational constraint. 2. Translational constraint. 3. Motion inputs, motors. According to this hierarchy, the solver first looks for rotational constraints that can be removed to eliminate redundancies. If it cannot remove any rotational constraints, it will then try to remove translational constraints. If it cannot remove any translational constraints, it will then try to remove an input motion. If all these attempts fail, the solver will abort with a message instructing the user to check for redundant or inconsistent constraints in the mechanism, or to see if it is in a locked position. Let's consider an example of the door assembly for the case study. It consists of two parts, a door and a frame. The door is connected to the frame using two hinge mates. We will analyze the door mechanism to understand the redundancies, their effect on the motion study, and how to remove them. For the given model, we will determine the forces on the two hinge mates as a result of the weight of the door. We can calculate the degrees of freedom within SolidWorks Motion using the degrees of freedom command. Consider the following example. The plate is connected to the fixed frame using a hinge mate. The only floating part is the plate, therefore it has 6 degrees of freedom. The plate is also connected to the frame using a hinge mate, hence it will remove 5 degrees of freedom. So the Grubler count, which is also known as the total estimated degrees of freedom, becomes 6 minus 5, that is, 1 degree of freedom. Since the plate can rotate about the vertical axis, the actual degrees of freedom for the mechanism is 1. The total number of redundant constraints in the system is therefore estimated degrees of freedom minus actual degrees of freedom, which is equal to 0. This means the system or mechanism has 0 redundant constraints. Let's see how to set up a motion study and measure the mass of the door assembly. Click Show Me to launch a demonstration video. We have opened the file entitled door.sldasm. In the assembly, both components are fixed and have 0 degrees of freedom. Fixed components are locked in place. Therefore, we will float the door so that it is free to move. Right-click the door and click Float. To save time, we have added 2 hinge mates between the door and frame. Now we will check the door weight using mass properties. The weight will also be measured at the hinges once the simulation is run. Click Mass Properties. Right-click the door assembly, clear it from the list, and select the door part from the graphics area. Click Recalculate. The mass of the door is approximately 28,000 grams, so the vertical force of the door is 274.8 newtons, assuming gravity of 9.8 meters per second squared. Click Close. Let's create a motion study. Click the Motion Study 1 tab. From the Type of Study list, select Motion Analysis. Click Gravity. Add gravity in the negative y direction. Click OK. Now we will change the study properties. Click Motion Study Properties. Set frames per second to 50. Make sure that Replace Redundant Mates with Bushings is cleared. We will discuss this option later. Click OK. Right-click Key Properties, and then click Edit Key Point Time. Click Edit Time, adjust the key time to 1 second, and click OK. Click Calculate. You can see that there is no movement in this assembly, which is what we expect. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about setting up the motion study. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed the simulation. Click Next to continue. Rather than manually calculating the DOF, we can calculate it within SolidWorks Motion using the Degrees of Freedom command. When we solve a motion study, only then does the DOF command become active. Let's see how to calculate degrees of freedom within SolidWorks Motion and plot the reaction forces. Click Show Me to launch a demonstration video. In the previous Show Me, we have calculated the study. Notice that, in the Motion Study Feature Manager, the Mate folder reads Mates, 5 Redundancies. Right-click the local Mates folder and click Degrees of Freedom. This opens the DOF dialog box. We can see the number of moving parts, number of mates presented as joints, total number of the estimated and actual degrees of freedom, and the total number of redundant constraints. SolidWorks Motion calculates 5 redundant constraints. The mechanism is over-constrained. The reason for this is that a second hinge mate is trying to constrain the same degree of freedom as the other hinge mate. Numerically, one hinge mate is sufficient to simulate the hinge condition. But this may not be enough, especially when reaction loads at both the hinges are to be calculated. In order to obtain a unique solution, the program is forced to remove the 5 redundant constraints. The selection is made internally without user intervention. The removed redundant degrees of freedom can also be found in the list. Close the Degrees of Freedom dialog box. Now we will review the force solution in the joints to reveal the consequence of the redundancies. Remember, the weight of the door is approximately 274.8 newtons. Gravity acts along the negative global y direction. The two hinge mates should share this load equally. Let's verify this. Click Results and Plots. Click Forces as category, Reaction force as subcategory, and Y component as reaction force magnitude. Scroll down Motion Study 1. And click Mates, 5 redundancies. Then click the second hinge mate from the motion tree. Click OK. When we define the plot, we will be warned. The warning indicates that redundant constraints in the analysis could make the results inaccurate, and bushings can be used if we would like to rerun the analysis. As redundant mates are the subject of this lesson, we will see what happens with the redundant constraints. We will switch to bushings for the next analysis. Click No. Reaction force on the second hinge mate is 0, which should not be the case. Similarly, let's plot the reaction force for the first hinge mate. Click Results and Plots. Click Forces as category, Reaction force as subcategory, and Y component as reaction force magnitude. Select the first hinge mate from the motion tree. Click OK. On the first hinge mate, the reaction force is 274.8 newtons. It can be seen that one hinge mate carries the full force of 274.8 newtons, while the other one carries no load. The distribution of the forces between the two hinges is incorrect. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about calculating degrees of freedom within SolidWorks Motion and plotting the reaction forces. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed the simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. Redundancies may lead to two problems. The first problem is solver failure, which means the motion solver is not able to solve the motion study. The second problem is incorrect force calculation. The first problem can be minimized by using mates which closely represent the mechanical connection in a real product, or by using simpler mates, such as point on axis. The second problem can be minimized by manually modifying the mates to remove the redundancies in the requested location, that is, by using flexible mates. In this approach, flexible mates are used in place of mathematically rigid mates. The stiffness of the mates in the respective directions decides on the distribution of the reaction forces. You can add flexibility to the mates either by using motion study properties or editing each local mate manually. The first approach is global and may work in most situations, while the second approach is local and works in all situations but can be time-consuming. When you make a mate flexible, The mechanism will be updated to have a bushing representation of the basic mate type instead of a rigid constraint. Please note that motion and frictional properties of the mate are not affected by using flexible mates. Although using flexible mates is one of the options that can be used to remove redundancies, it does have some limitations. In some models, using bushings will increase the solver time because of induced dynamic effects. Advanced mates do not support mate flexibility. If the mechanism starts in a dynamic condition, there may be a spike in initial forces as the model reaches initial equilibrium. The spike is generated by initial conditions of the parts not balancing and the bushings resisting rapid changes in force and acceleration. Optimum mate stiffness and damping characteristics may need to be entered. This may require an iterative approach. Let's see how to replace the redundant mate with bushings to correctly solve the study. Click Show Me to launch a demonstration video. In the last Show Me, it was observed that reaction forces obtained at both hinges were incorrect. The reason behind this was that the solver found the second hinge as a redundant constraint and it removed that constraint. Hence, no results were calculated at the second hinge. The entire weight of the door was balanced by the first hinge. Now, we will use the Replace Redundant Mates with Bushings option to correctly solve the door example. Click Motion Study Properties and scroll down. Select Replace Redundant Mates with Bushings. Click Bushing Parameters. If we want to change the stiffness and damping values, we can change it here. For now, keep the default values and click OK to close the dialog box. Click OK again to close the Motion Study Properties Manager. Click Calculate. Notice how the Mate icon in the Mates folder of the Motion Manager changes. The lightning indicates that the flexibility of this mate was forced by the software rather than manually specified by the user. Let's review the results. The Y component of the reaction force for both mates now shows a value of 137.5 newtons. The weight of the door has now been correctly shared by both of the hinge mates. Click Save and close the file. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about replacing redundant mates with bushings. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. That brings us to the end of this demonstration. Click Next to continue. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module, Understanding Redundancies. Here are the key takeaways from the module. Click each tab to learn more. Here is a chance for you to practice what you have learned. Offline exercises are available for this module. To attempt these exercises, you must have access to a SolidWorks installation. To complete each exercise, download the self-extracting executable file from the eCourse Details page on mysolidworks.com. This file contains the sample models and exercise PDF file for every module in the e-course.